and phase will get established 1 decade after the second corner. So this is, sorry again, I missed the peak will be right over here, right? So this is the phase plot. This is the magnitude plot. By the way, this is 0 dB. This is 0 degree. This is 0 dB. This is 0 degree phase, right? So similarly for the lag compensator, even if you do the similar calculation, you'll find that this depth will be 20 log alpha. This frequency corresponding to this maximum phase omega phi minimum, where maximum phase is being subtracted, not added. It will be 1 over tau alpha square root, exactly geometric mean between the corners. And the magnitude corresponding to omega phi minimum, the phase will be sine phi minimum. It will be alpha minus 1 over alpha plus 1, and this will be magnitude over here will be 10 log alpha, and full established magnitude will be 20 log alpha. Obviously there will be a negative sign with this, not a positive sign, right? And this 5 sine phi minimum, and phi minimum will become negative. So I guess there will be some negative somewhere, although in the designing it won't be used. I guess I should put a negative sign over here. Yeah, designing techniques for both are different, so perhaps this formula will not be used, but in the lead compensator, we'll use all these formulas to design the lead compensator. And just I'm gonna just go over very quickly how we'll design the lead compensator. We'll just, because we are adding the compensator in the loop transfer function body, we are adding the compensator directly in the loop transfer function. So original position of loop transfer function, pole and zeros will stay the same, plus we'll add more poles and zeros, one more pole and more zero of our lead compensator in the loop, and it will change the magnitude and phase plot of the loop transfer function accordingly. So because compensator is added right, like over here, compensator is in the loop transfer function. So if I have a loop transfer function without the compensator, whatever is in the loop without compensator, and if I add a loop compensator, the Bode plot of both will just add and subtract to get the overall loop transfer function Bode after the compensation. So, and the basic idea of the controller methodology of controller compensator design is that we'll play with the phase margin. Remember, phase margin is a term which is used for loop transfer function. And similarly, gain margin. It is only for, these two terms are only for loop transfer function, and on the loop they define the stability of closed loop system. In addition, means if we have a positive value of phase and gain margin, system will be stable, right? So what we'll do, we'll add a compensator to bring stability to the system. In addition, we went through another relation. We derived that, in fact, that damping ratio is 0.01 of phi phase margin. So this is the relation between the steady state response and transient response. Steady state response of a loop transfer function and transient response of a system. Damping ratio tells us that yeah, what will the system overshoot, and phase margin, and it is related to the phase margin directly with certain assumption that system will be either a second order or a dominant second order. But still, it works very well with approximation. So we'll use this connection and we'll try to fix the phase margin of the system, and indirectly we'll calculate the damping ratio of the system. If there is a requirement for the system damping ratio, we'll try to fix the phase margin. And phase margin is the terminology which is only for the loop transfer function. So we'll add on the existing system loop transfer function body and other body which is the body of the compensator, and we'll try to get the resultant of both bodies as per our uh, requirements, right? So we'll see in the lead compensator design in the next lecture, and till that time, thank you so much, and I'll see you next time.